while we are waiting, are there any questions from the previous lecture? Someone is Santosh waiting in the waiting room. Santosh, are you there? Ah, okay, okay, okay. Okay, let's get started. So today's lecture will be more on the future prospects, and which will also include Ligo India. So in the first two lectures, we basically saw how gravitational waves are produced, what are the astrophysical sources, and how they can be detected. Now here, but then we just started the field of astronomy. There is a lot more to do. And here are some science cases listed here, which can be used, which can be probed with the next generation detectors. So in astrophysics, for example, we have detected neutron stars, but the neutron stars are complex systems. They have uh, there are different models for the equation of state and so on. So black holes are much simpler. Neutron stars are more complicated. But then we can see what is going on in neutron star, but we cannot see what is going on in black holes. So that makes neutron stars pretty interesting. Then there could be different phenomena which are going on, which can be probed with more and more observations. With only one observation, it's difficult to say exactly how these systems are. Then there is cosmology distance ladder, which I said that we can have a better estimate for Hubble constant and so on. And also fundamental physics, that whether general theory of relativity is the ultimate theory of gravitation or not, that should be probed. But there are more things, like for example, if dark energy, about which we don't have much idea, but it has to be put kind of by hand to explain what we observe. With precise measurement of Hubble constant and perhaps the distribution of objects that we measure in the universe, we observe in the universe, we may be able to get better uh, estimate for the dark energy equation of state, or rather, like how the dark energy varies with redshift. That is the nature of dark energy in the earlier epochs and now. It may be very simple. I mean, it may be dark energy is just a cosmological constant and things like that, but we don't know what it is. And then, of course, the surprises. If you remember in the first lecture, I mentioned that as we with different new windows of astronomy, we get uh, not only get higher resolution images of the universe, but we also there are surprises which dramatically change our understanding of the universe. For example, I gave some examples like when we detected pulsars or the expanding universe, even the accelerated universe, uh, cosmic microwave background, all those things. So the idea is that gravitational wave astronomy started uh, with it had an eventful beginning. In fact, more than what we expected, much more exciting than we expected, and we have to take it forward over the next decades to probably centuries. So what is happening right now? This picture again I kind of showed in the last lecture. So this is where we are. These are the terrestrial detectors, and they cover this. Uh, so this is basically the 100. Um, so you can see that this is the wave frequency here, and the period is also mentioned there. Fortunately, the unit kind of comes here. But yeah, so this is in hertz. This is the frequency in hertz. So this is 100 hertz. Okay, like in the audible band we are observing right now. But they are also, we have observed only one kind of source so far, and those are uh, merger of compact binaries. There are more sources which are predicted, but we have not observed them. Supernova pulsars, we talked about them. Then if we go to space, we can observe bigger systems like supermassive black hole mergers and extreme mass ratio in spirals, which we talked about. That is a small black hole going around supermassive black holes. With even lower frequency, with pulsar timing arrays, we may be able to see supermassive black hole in spirals. The merger may happen in the space-based part, and the in spiral may happen in the pulsar timing region, which is kind of nanohertz band. Then there is this uh, background from the early universe, which was generated perhaps when the universe was a fraction of a second old. That would be the earliest picture that we would be able to get for the universe. The earliest picture right now, what we have is the cosmic microwave background. That comes when the universe was about 4 lakh years old. We can go much beyond that. That's close to fraction of a second. If we can detect this primordial gravitational wave background, the signature of this background can be found uh, is there in the cosmic microwave background B mode polarization, but detection of it is challenging because our galactic dust also creates such signature on the CMB. So that will be an indirect detection of this background, but then there could be a direct detection which may happen in any band because this signal is kind of present in every band, but with more probability in the decihertz band, which is here, because there is a lack of astrophysical foreground in this region, that there may be more hope in that band. Also, we want to make you should be able to make a map of the universe. Like, you have seen these surveys, these maps of the universe in different frequency bands in electromagnetic astronomy. So this is the radio image, and the frequency increases, and here it is gamma ray. So from here to there, all these maps are made in electromagnetic astronomy. In gravitational waves, we have nothing like this yet. We only have a few transients here, that is not even permanent. That is few dots here, but those dots are also not permanent. They are only like 1 second long, or maybe tens of seconds long at least right now. So this is the situation right now. We want to get a persistent map of the universe. So this may take, as I said, decades, years, certainly years, but decades to maybe centuries. So moving on, so here we are right now, like in Galileo's original telescope sort of situation where he observed few planets. Here we have observed few black or compact binary wave mergers. That is where we are, and this is the future. This is where we are in electromagnetic astronomy from here to here in more than 4 centuries. And I hope gravitational wave astronomy also evolves in this way. And many of you may actually contribute in this effort. So, how do we? What are the immediate plans? This is the power spectral density for the initial detectors, which I mentioned in last lecture. It did not detect anything. This is the first generation detector, but they showed the technology. They demonstrated the technology, which enabled funding for the advanced detectors, which are 10 times more sensitive, and they have detected, and it is going to operate for several more years. But meanwhile, each one of these, so this detector, for example, took at more than 10 years. I mean, basically the planning started, including planning, it took 30 years to get this. And then 10 more years for this. Maybe let's say 20 plus 10. And then that, so we have to start, but these two were housed in the same housing, same vacuum. Now to go beyond, we need bigger detectors and different sites, because you need much bigger land. So the process has to start now. So in the next 20 years, the target would be to build these detectors. This is, I'll tell you what these are. So these are third generation detectors, which are basically one Einstein telescope in Europe and Cosmic Explorer in the US. So this is how, so what is going to happen with these detectors? So this is how the sensitivity is going to improve. You can see that there is something called Ligo A plus here, which will be the next generation, next major upgrade for the present advanced LIGO detectors in the same vacuum. And Voyager is another upgrade, which will be probably the ultimate final upgrade for the present LIGO detectors. And then we will get this Einstein telescope and Cosmic Explorer in the next 20 years. Now, how things are going to evolve astrophysically. So let's say we are here, okay, somewhere in the center. This GW170817 is not the center. It was just very close to us. It was just 40 megaparsec away. That's why it looks like it is almost at the center. Now, no, sorry, yeah, that is right. That yellow star is the GW170817. Now, what is going to happen is that as the detectors improve the sensitivity, so this is where we are, like slightly, yeah, we are here. This is O3. See this one, and here this one. This side is for neutron star binaries. This side is for black hole binaries. As the sensitivities improve, in the next, like let's say about 3-4 years, we should be able to reach here and see that a large number of sources, binary black hole mergers, will be observed there. We are kind of in a very quiet region right now. I mean, this is nothing special about our position on the universe. It is just that we are limited in the local universe, meaning the redshift of which we cover is very small. As you go to higher and higher redshift, universe becomes denser and denser because the expansion is less, and also lots of stars formed at redshift of 2 and 3. So because of all these reasons, this part is much more dense. So then we will get a huge number of black hole binary merger once we go to A plus, and that is supposed to be the target sensitivity for LIGO India as well. Then there will be upgrades to Voyager, which is here, and this would essentially cover all the black hole mergers in the universe. But even with Voyager, you can see neutron star mergers are still not that well covered, and that is why we need a next generation detector, because electromagnetic follow-up is the key in order to get the Hubble constant and other astrophysical information to very high precision. And that is why we'll learn about black holes from here, and then that will tell us many things about the structure formation, etc. But with this, it will be much more exciting. And here, this green one is Einstein telescope, which will already give us a lot of binary mergers, and the Cosmic Explorer is essentially going to nail the whole thing. So this is the present plan with ground-based detectors. And these are the kind of concept designs which are going on. So this is Einstein telescope's concept. It will be underground, about 100 to 200 meters. It has, so that the seismic vibrations are a little less. The length will be probably 10 kilometers. It could be in a triangular shape and things like that. So this is what the present plan is. It can change. And this is what Cosmic Explorer is proposed. So this is going to be 40 kilometers. It's like an extended LIGO. And you can see the comparison between the present LIGO and Cosmic Explorer. It's extremely big. 40 kilometers is basically bigger than any normal sized cities, like except maybe for the elongated Bangalore and Mumbai sort of cities, which have very long, the suburbs are very far away. And this is a comparison with Einstein telescope. But then this is going to be the plan for the next 20 years for the ground based one. Now let's see what happens in space. The target for space is to launch this detector called laser interferometer space antenna (LISA) in around 2034. Now, if you go to, as I already mentioned, that you need to in order to counter seismic noise. Basically, if you want to have low frequency measurement, you have to go to space. There is no other choice. And this arm length kind of determines that what should be the wavelength that will be probed by these detectors. For LISA, this arm length would be like million kilometers of the order, and there will be 3 spacecrafts which will follow Keplerian orbit and go around the sun. So this is basically what the plan is. Now, there was a mission called LISA Pathfinder, which was launched in 2015, and to test some of the key technologies that will be used in LISA. The target for that was that if LISA Pathfinder could meet this requirement, that it can achieve this noise, then it will be a very strong proof that we would be able to build LISA, and it will be funded. LISA Pathfinder not only uh, fulfilled this requirement, its noise actually became more than what is LISA's requirement. Of course, in that specific sense of certain kind of noise. And this is just the LISA requirement, and LISA Pathfinder essentially went even beyond whatever was required for LISA, and hence this project is going very well. So what are you going to do with LISA? So LISA will enable multi-band observation of binary black hole merger. That is, it will basically predict when a merger will happen in the ground-based detectors band. It says LIGO band, but LIGO may not be there at that time. So something else will be there. But this is the idea. So the binaries in spiral for a long time in the lower frequencies, and LISA will see them, and then by observing those, one will be able to predict that how the frequency is going to change with time for those binaries, and when they will enter LIGO, and then they will merge, and this will be the ring down. So this is what LISA will enable, and of course LISA will have its own science, own target observations also, like supermassive black holes, etc., which will only be able to see with LISA. They will merge here. Okay, now this is one of the interesting things that we see what LISA is going to see. So this is an animation where this is an extreme mass ratio in spiral. A small black hole goes around the large black hole. When the black holes are of kind of equal mass, the system is simpler, meaning it looks simpler. That is, it goes like planets. But when these objects goes at very high speed near a supermassive black hole, the orbits are far more complicated, and then something interesting happens here, as you will see. Now see, this is showing the days before merger. Of course, it is highly accelerated in time. I mean, otherwise it would take 200 days to play this video. And look at the speed. It is 0.2c, so very high. This box is going to shrink with time. The last cutoff was very interesting, that the sound suddenly stopped. And that is because the small black hole entered the event horizon of the bigger black hole. And that would be a very sharp test for the existence of event horizon. Actually, the small black hole does not really go inside it from our frame. It becomes infinitely redshifted. Okay, so now let's see some more things which we need to which we can see, hope to see with the future detector. So I think yesterday or no day before yesterday, maybe somebody was asking about confusion noise, and I told you about the stochastic background that is created by the universe. For example, these are the backgrounds which would be created for different set of astrophysical parameters, and that we may be able to see them in LIGO. So each of these lines show the spectrum of a stochastic gravitational background created by different astrophysical models. And you see that these models and this is kind of showing the sensitivity of the present detector. So these ones would not be visible, these one may be visible, and things like that. Now, and this plot also shows that after how many months of observations we may be able to detect such a background. Why is it important? The thing is that I'll come to that very soon. So this kind of background can be created by different objects. For example, we predicted how much would be this background uh, uh, created by extrasolar planets. The exoplanets, uh, there are many exoplanets in our galaxy. Initially, it was not known, but at some point, few years back, we realized that actually there are probably 1.4 or something exoplanets per star in the galaxy, and the galaxy has like 11 stars. There's a large number of them. When these planets go around their host star, they create gravitational waves, but it is extremely small. But because this number is so large, in the end, you may end up getting a signal like this. Okay, you see these red dots and yellow dots. So the signal could be like this, which is comparable to the same signal from the inflationary background. And this is LISA's sensitivity. It is not detectable by LISA, but as you saw, that LISA Pathfinder sensitivity noise was so low. It could be maybe that at some point LISA or maybe some other future detector will be able to see this. Now, why do we want to observe these things? See, ultimately, we want to. This one of the primary interests is to observe this signal, the inflationary background. So, if we don't, but to confidently detect this, we need to first understand what are the foreground sources, and that is one of the important things. So, once we know the astrophysical foreground, then we know what we have observed if there is a hope for detection for the inflationary background. So this is this current present situation of the present understanding of the universe. That we have different phases of the universe, and this is the earliest picture of the universe that we have in hand. We do not have any real observation of this part of the universe, and primordial gravitational waves can give us some information of what happened here. Also, as I said, there are major gaps in cosmology. The inflation is kind of put by hand. So an observation of the universe of the inflation of some radiation from the inflationary epoch is very important. Similarly, uh, this um, the distribution of matter. If you see that the universe has about 30% dark matter and 70% dark energy. Okay, ordinary matter is very small. Even that is not completely understood, but this almost 95% content of the universe is absolutely not understood. So there is a whole lot of things we have to understand. Okay, and gravitational astronomy can help us in that. Now, to probe the primordial gravitational waves, there are many missions which are many things, many windows where people have looked at, but only this one kind of has the sensitivity to see it. It's called Big Bang Observer, but that project is not funded or even progressing. There is something called DESIGO, which may be able to do it, but then the funding situation there is also not clear. And this is one of the windows which can be very interesting. Then there is this part, which is the where a future CMB mission, like earlier it used to be called CMB pole, may be able to probe the signature of those background in the cosmic microwave background polarization. So here is the this was the Big Bang Observer mission which was proposed. This will consist of these constellations of spacecrafts. Okay, so three here, and six there, which would so each one of them is an interferometer, and then you can cross correlate data from all these interferometers to get a very high sensitivity. This was a next generation CMB mission which was proposed. Now there is a CMB Bharat mission which has been proposed. Then there is a this is the this has pretty good chance of flying, but then right now it is not funded, and maybe there will be other countries, including India, which will be interested in building something like this, which is very similar to, not very, okay, which is similar to this Big Bang observer. And then, there are some work which has gone in that direction. Basically, the primary target would be to detect the primordial gravitational background. Okay, so now I will, so these are kind of the future. Okay, this will take decades, and we don't know when they're going to be funded, etc., except for LISA. So what we have to do now, in concrete terms, of course, we have to write proposals, so to see whether any of these detectors or projects can get funded, and then we have to work towards that. But in parallel, we have to keep working on the ground-based detectors, and our primary target, of our primary interest, of course, is to build Ligo India. So let's see why we want to do that. Achha, before that, are there any questions? Okay. All the question is that all the spacecraft clusters of LISA BBO, etc., will orbit the sun. Yeah. So the ones I showed would orbit the sun. But then there are other missions proposed. Like there are two missions proposed from China, where I think one is orbiting the sun and one is orbiting the Earth. But this design may not work if you don't orbit the sun, because things have to be these clusters have to be quite far away. Otherwise, the correlation may not give you very good result. Okay, I don't see any other hand up, so I will move ahead. So we need a network of okay, the question is, they will be in Lagrange point. Okay, no, they are not going to be in Lagrange points, because these are quite far away. So and there are three, so it cannot be in a Lagrange point. And these are pretty big. So okay, so I think the thing is that these are billion kilometers. So the Lagrange points would be much smaller. The stability region, yeah. Okay. Yeah. So now you see that these are the, okay, there is one more question. By how much times space antenna will detect? So that varies. So you see that number is given here. For some sources, this is 1 year. For some, it is tens of years. So one of the problem there is that this is too long. That is, you have to wait for years in order to see a source here. LISA is going to fly in 2035. 10 years from then is like 2045. So maybe the third generation gravitational wave detectors will be operational by then. But again, if we want something in the quicker terms, we may want a detector here. Again, that is basically in the decihertz band. If there is a detector here, then you can see that the predictions will be much faster, because this is 1 hour. So you would be able to predict like minutes to hours in advance if something is going to be. Decihertz is actually here, this one. So typically the average would be in days. In days, let's say in basically in days times to hours time, like this. Einstein telescope cosmic explorer will cover up to this, and then you can see here. Okay. Any other questions? Okay. So we basically need a network of detectors in order to have confident detections and to localize a source on the sky. So what we mean by confident detectors? So I think some of you also asked, and many people asked, that how do we know that what was detected in LIGO is a gravitational wave signal? Well, the reason is that there were 3,000 kilometers away, two detectors detecting the same signal, signal of that particular shape at the same time, that is within milliseconds distance, time difference, uh, which are 3,000 kilometers, and the detectors are 3,000 kilometers away. Seems like it will be a very, the probability of such thing happening is extremely low. This is like 1 in 65,000 years. And that's how the detection confidence grows when there are more than one detector. But the thing is that the detectors are not sensitive to all the directions at the same time. They do get signal from every direction, but sensitivity is large in some directions and small in some directions. With more detectors, those holes on the sky kind of get filled. But then there is the most important thing is about the localization. Now, in this is the map or sort of the sky map of different events which were observed by the LIGO Harpo detectors. I think, okay, by the way, you probably have noticed that we call them events instead of source, because a source like the sun or the moon are sort of like persistent. But these things are not persistent, they are transient. That's why we call them events. Okay, there is a question. Hmm, how is the marginal location fixed in LIGO absorption? Yeah, I'm coming to that. So what happens is that it is in the present detectors, you see these huge angles. These are basically the regions on the sky where the source is localized. So if you can see carefully that this is basically like a band. It's almost like a band on the sky. Okay, maybe half. So one part is here and one part is there. So why is it like this? So basically, it is like GPS satellites. This localization is done by observing the time delay in the signal arrival time in two detectors. So if the two detectors observe the signal exactly at the same time, then you know that the signal would be meaning without any millisecond delay also. The signal will be on the ring on a ring on the sky. This ring could be here, this ring could be here, but it will be symmetric about the line joining these two detectors. In order to really pinpoint where the source is, you need a third detector. This is how GPS works, right? You need at least three detectors to localize where you are. Similarly, for gravitational waves, these rings are basically forming because there are two detectors and they are looking at something like a ring on the sky. But since the detectors are not so sensitive in some regions, these parts are ruled out. So this is how it is. It is basically a ring. But when you have a third detector, which happened for this one and this one, this is an old plot, but then that is better. Now it is too crowded. You see that the resolution, the angular resolution is much higher, much better. They are much smaller. But even then, these are pretty big. These are about like 20 square degrees or something. So you can easily fit 20 moons here. For example, this was the first detection, this green one. You could fit 1200 moons in this. This is so big. Now, what is this orange ellipse showing? So when the first detection happened, if LIGO India was operating at that time, the error circle would be this small. Okay, the localization would be very precise. But why do we want this localization? What is the advantage? I think I told you in the last class that if this source GW170870 was not localized to this small circle, we would not be able to get the host galaxy. We would not be able to get the redshift, and no other follow-up observation could have happened. The thing is that the electromagnetic observatories have very typically, when they are very sensitive, the big telescopes have very small field of view. So you need either you have good sensitivity or large field of view. You cannot have both at the same time. So what happens is that if you really want to observe some region very deeply, you need to scan the whole region in a very short time so that before the source fades. And that's the primary goal. Now, if the circle is not small, it is large, by the time, like one of these, by the time you scan the whole part, it will probably be a week or something. This one is just manageable to do, but even this is pretty big. People want to reduce it much smaller, like very small. Then it will become much easier to find these candidates, these follow-up candidates, that is those events which can generate electromagnetic waves. And this is one of the primary motivations for LIGO India. What happens with LIGO India is that, you see, this is the globe. Okay, we are looking at the North Pole here. This is America. This is parts of Asia, and here is India. This is India. You see. So you see that for the two LIGO detectors, the distance is 10 milliseconds, and here is the Virgo detector. The distance is 25 milliseconds or 26 milliseconds. I mean, you can express distances in milliseconds, like you have to multiply by the velocity of light in order to get the proper distance. That is 10 milliseconds means 3000 kilometers. When LIGO India comes, it becomes that now not only, so there are three baselines with Hanford, Livingston, and Virgo. Okay, this is LIGO. So this is like a triangle. But with, like, if you put LIGO India, see the number of baselines becomes 6. There is three more baselines which come, and each one is pretty long. These two are much longer than this, and even this one is comparable to the longest what we have right now. So with this, as what happens in radio astronomy, we'll get much higher sky localization, much higher resolution in sky localization, and there are more baselines. So the sky localization accuracy will be very much higher. And there is another way to sort of see that, on the globe, how it looks like. These are the baselines, even though we have to consider the straight line distances between them. There are, okay, so this is a very nice way to represent what exactly happens with these detectors. So suppose we have two detectors at the same place, Hanford, and there is one Livingston and one Virgo detector. With those detectors, these will be the error circles on the sky. So see, these are very big, and there are these crosses where the detectors are not sensitive at all. And these areas are very large. But with LIGO India, if you just replace one Hanford detector by an Indian detector, the error circles become much smaller. And that is the primary advantage of LIGO India. Of course, this is assuming that LIGO India has similar sensitivity as the other detectors, and it has to operate simultaneously. So which means that the detector really has to start operating, operating along with other direct detectors, and it has to be done very soon. There are many other figures of merit, like, which I kind of mentioned, that the horizon distance overall increases, because if you have more detectors, you have more reach, the overall sensitivity in a given direction increases. Then the detection volume increases. That is because I showed that spherical detector volume earlier, but in practice, since the detectors are not sensitive equally in each direction, that volume is not really spherical. It has some distortions. And with another detector, that improves, it becomes more symmetric, and the reach increases, so it becomes much bigger. And then there are many other, like for example, the triple coincident detection. So if you have detect with two, localization is bad. So how much would be the improvement with triple coincident detection, that is enormous. You see, this increases by a factor of 6 or so compared to the two LIGO detectors. So these are the kind of sky coverage increases and all those things happen. Anyway, so the point is that there are many advantages of LIGO India. So what are we going to do about it? Now this is the site is will be located near so the primary site is at Hingoli in Maharashtra. So several sites were what is that called? Meaning visited and surveyed for the detector. Now there are certain very strong criteria to find a site for a detector like this. It has to be in a quiet region because human movement creates a lot of noise. So, for example, the LIGO detectors, the day and night time noise differs because of that. Weekend noise is different. This has to be far away, but it cannot be so far away that people cannot access the site. So there has to be an airport, maybe in, let's say, 50 to 100 kilometers. But then there should not be much development in that region. It should be far away uh, from the seas because the ocean waves can create noise. Uh, Preferably in a seismically quiet region, which is what the Deccan Plateau is. Earthquakes are fine because they are rare, but on the other hand, some of these regions are really seismically not quiet. So all consideration putting into place, and of course there has to be land availability and things like that. This was one of the primary place where it seemed it will be feasible to build the detector, and that site is indeed pretty quiet and so on. Now, why government wants to spend money in such missions? Okay, so of course, as I said, that science is one of the primary goals of humanity. Historically, also, in coming to more day-to-day life, those countries which spent uh, more for research did well. They developed faster because scientific thinking takes the country forward in different ways, like technology, etc. But more concretely, these sort of mega science projects, especially since LIGO India is going to be on Indian soil, connect several frontiers in technology. So LIGO India, for example, will require quantum measurements, laser physics, vacuum technology, optical engineering, sensor technologies, control systems, then a lot of computing. Okay, so all those things, so all these frontier areas would share a common platform from which people can come up with different other projects, not necessarily in gravitational waves. And of course, gravitational waves will connect all these other fields of astronomy as well. So these are the motivations why this this kind of projects become more helpful for the country than just then just the science output of this kind of detectors. Okay, now moving forward, I'm almost. Oops. Oh, okay. My keyboard got locked. There was a problem with the keyboard. Okay. So what is happening is that several institutes, the project will be implemented by four major uh, institutes in India. They are called RRCAT, the Rajaraman Center for Advanced Technology, uh, Institute of Plasma Research, IUCAA Institute, and DCACM, which is in BRC. So these institutes, they are the primary, they will do the primary execution of the project, but the project will be done by a very large community. The science and the technology development, all those things will be done by different institutes across India, like IITs, ISSAAs, universities, and so on. And my Ayuka basically does this host meetings to bring all these researchers in a common platform from where they can they can uh, communicate, collaborate, and so on. Ayuka hosts a large computing facility which is used by different uh, institutes in India and abroad. I mean, we are part of the international Ligo scientific collaboration to do several data processing. This is one of our present commitment to the community. I mean, of course, we enjoy the data, but then we don't have a detector right now. So these are different ways we can help the community. There are different things which one can do. Basically, there are scope for cutting edge technologies in a different way. This is just one example. So my student Nikhil Mukund, who picked up uh, different skills on machine learning, and uh, these are some of the ways in which for different things these machine learning techniques were used, like earthquake warning system, that you should be able to see you predict that an earthquake is coming, so that detector goes to a state where then it can come back to the normal operating point very soon, because an earthquake would kind of destabilize the detector for some time. It may take a little longer time otherwise to come back, and things like that. Anyway, without going into this, I will now wait. Uh, Santosh, please mute. Okay, let me try. Yeah. Okay. So the summary here is that gravitational waves have been detected and started a new era in astronomy, and the start has been very exciting beyond what ever beyond what we expected. And now this is a new window of astronomy which not only provides a better picture of the universe, but gives us makes a dramatic shift in our understanding of the universe. And also for young people, it gives the opportunity to take the field forward. There is a huge amount of work to be done. So worldwide effort is going on to develop detectors, analysis techniques, signal models. I did not talk about this, but in order to, when I showed this uh, match filtering demonstration, that if you knew the shape of the signal, you could dig out from the noise easily, that requires the signal model. To get the signal model solving Einstein's equation numerically is very challenging. You cannot solve those equations when the binaries are very close numerically, because the speeds are very high. It is very difficult to solve. I mean, analytically. So you have to solve it numerically. Sorry. Analytically, you can solve when they are far away or in the ring down phase. I think I mentioned that. So this is one of the major things which are going on in India. Earlier, numerical relativity was not so much. The presence was less in India. I mean, hardly there. But now there is significant numerical relativity activities also going on. Now, advanced and other future generation, that is the third generation detectors, are progressing rapidly. Of course, they are not fully funded, but there is a lot of research going on. Now, the hope is that in the next few years, there will be a detector in India, and also in the next decade, there should be space-based detectors, which should open up another window in gravitational waves. Like in electromagnetic astronomy, there are different windows: X-ray, infrared, ultraviolet, and so on. Gravitational waves, we are right now only in one window, which is this audible band, and hopefully there will be millihertz window, decihertz window, nanohertz window. All those things will open up in the next decade, at least to some extent. Like astronomy, Galileo's astronomy brought renaissance in astronomy. We hope gravitational waves will also bring major change there. Okay, I'll stop here. Let me know if there are questions. I don't see any questions. So, okay. While you think about questions, I can share a video link which you may watch whenever you are free. When this lectures were in person, I used to show this video. So okay, I think one thing I will do for everyone is to share this link. You can watch this whenever you want. Okay, how do we find out the sensitivity of the LIGO detectors? Uh, Basically, what happens is that you are continuously getting a time series output from the detector. If you take the part spectral density, that is your sensitivity. So even though I said that that picture that there is an interferometer, some gravitational waves are falling on it, and then the arm is changing like this and things like that. Actually, that does not really happen. What is done is that you want to maintain the resonance in the detector. So basically, it is operated in a feedback detector mode. The signal which is required in order to keep the position of the mirror at the same place is considered the primary signal for gravitational waves. Uh, so basically, what happens is that the gravitational waves are falling on the detector. It is trying to move the mirrors, and you sense how much the mirror is trying to move, and by sensing that it can be fed back so that the mirror stays there, so that the whole power build up does not go away, because in a fabrical cavity, if you remove the mirror, then the power goes down and then the sensitivity will fall, and this feedback signal is the gravitational signal, and that meaning which also has the other noise like seismic noise, etc. Also, so the sensitivity is basically the spectrum of that signal. By looking at that, you know that how much gravitational waves we can detect. Now, you could say that well, gravitational waves may already be present there. Well, we are not in such a situation that there is always a constant gravitational wave present. I mean, the gravitational waves are coming only like their detectable signal is present maybe for a second or two in a week. So most of the time, the detector is without any signal, and that is how you can get the sensitivity estimate. Yeah. Okay. I see much less number. Okay. There is one more question. Mm, okay. The graph of sensitivity of the LIGO detectors with respect to frequency decreases at one point, that is minimum, and increases. What is the reason for that? Oh, okay. That is, I think maybe you can look at this. I did mention this yesterday. Okay, let's see if I can show you the plot which I showed yesterday. So this is the plot. Okay, you see that here this is the seismic noise. Seismic noise falls as 1 by f square, and to the power n, where n is the number of stages in the detector. So this is basically 1 by f to the power 8 fall, the seismic noise. This part, this is the photon short noise. Generally, the short noise is white, so you would expect something like this. But then the Fabry-Pérot cavity creates something called a transfer function, which uh, brings this kind of pushes this up. This part is dominated by again some kind of sort of white noise, which is the thermal noise. So this is how the sum of this is plotted here ultimately. Okay. Then the next question is, uh, how does does earthquakes contribute to the if so, how do you, so when there is an earthquake, it is difficult to get usable data. Okay, so the detector goes kind of what is called out of lock for some time. uh, Lock means this, that you know what I said, that suppose you have a fabric cavity, you want to maintain the detector, the distance between the mirrors such that the resonance condition, that is length, is equal to half integral multiple so n lambda by 2, basically that relation is maintained. When earthquakes come, that relation breaks for a moment. So then the detector goes into a low power regime where the sensitivity is very low. But then it comes back, very soon it comes back to the normal state of operation. So during earthquake, it is difficult. But then there are many other glitches, which are called glitches basically. These are sort of very small duration noisy signal which creates uh, uh, this kind of bumps and so on in the detectors. Those uh, there are different machine learning techniques which are used to identify those. Basically, the point is that gravitational waves also create uh, essentially those noise blips, okay, noise glitches. Blip is actually one of those noisy glitch. So with machine learning, people identify those regions and then try to mask that. That is, you when you analyze, you kind of remove those parts, and this is how people deal with such noise transients. Okay, the short noise does not look like white noise, but perhaps close to it. Well, it is, if we were in a Michelson interferometer. Actually, this has something to do with the fact that is slightly more complicated reason is there here. So in general, the noise would be short, would be white. The short noise would go like this. It goes up because of the reason that, okay, let me show here. So here, what is, I showed this thing, you know, that when gravitational waves, sinusoidal gravitational waves fall on this ring of particles, it does this kind of oscillation. But the thing is that the one second, yes, uh, the thing is that the mirror, I mean, the time taken by photons to hit the mirror and come back in same ways could be, so as so you know this thing is doing like this. But on the other hand, gravitational wave frequency, see, when this oscillation is happening, there are many times photon is going like this. Now suppose the photon was very slow, so it is going exactly at the same speed. That is, when it is extended, it goes like this and it comes back again like this. Then you completely lose the gravity wave signal. The idea is to sample it rapidly, so that photon should make several trips before, while this is going there and coming back. Now this, but at higher frequencies, this breaks down. The time photon takes to, you know, actually there is a Fabry-Pérot, so actual picture is like this. So photon makes several trips and then comes back, I mean, on the average. By the time that happens, the wave phase changes for higher frequencies. So that when you fold in, you get a small increase, which is why it is not um, does not look white. What is the number in the top right center of your slide? This number, this number signifies a LIGO document number. That is, this slides generally we put it in this in the, it requires uh, Yeah. Yeah, it is sort of like that. Yeah, the aliasing. Okay, so this number basically says that it's a document number. I have to check exactly if we can call it aliasing. Maybe it can be. Yeah. It is basically like that the phase is changing while the photon does this shift. So the assumption is that phase is changing very slowly, and meanwhile you are just probing. Like you imagine a sinusoid, you are putting small bands there and probing. Then you get some dots, which gives you a sinusoid. But if suppose your measurement length goes covers the whole sinusoid, then essentially you get zero, because so that is what is avoided. Basically, if you choose the detector in such a way that for one half of the sinusoid you get some signal, then the other half you get some signal, and so on. So that the positive, I mean, it's kind of an optimal length. That makes it lambda by 4. The length of the detector should be lambda by 4, effective length, that is multiplied by the number of round trips in the Fabric cavity. Yeah. Okay. Any other questions? Okay. I don't see any other hand up. So we will stop here. Um, okay. All right. Bye, everyone.
Thanks, Sanjit.
Yeah. Over to you, Devarati. Bye.
Yeah, bye.